Organic compounds are composed primarily of carbon and hydrogen, with other elements such as oxygen and nitrogen sometimes present. Combustion analysis of organic compounds lets us use the mass of the products to determine the makeup of the molecule. To keep the analysis simple, we will stick with organic compounds containing carbon and hydrogen and sometimes oxygen, because the production of the complete combustion of these compounds is always carbon dioxide and water. To do the analysis, the organic sample is completely combusted in an excess of oxygen, ensuring that the products are carbon dioxide and water. The carbon dioxide and water are collected on an absorber, and their masses are then determined. The masses are then used to determine the empirical formula of the organic compound, and sometimes with sufficient information, the molecular formula can be determined. In the combustion reaction, X is the subscript for carbon, and it is also the coefficient for the carbon dioxide. As a result, the molar ratio of the carbon to carbon dioxide is 1:1. The corresponding mass ratio of carbon to carbon dioxide is the molar mass of carbon, 12.01 grams per mole, divided by the molar mass of carbon dioxide, 44.01 grams per mole. Also in the combustion reaction, Y is the subscript for hydrogen, and Y divided by 2 is the coefficient for water. As a result, the molar ratio of hydrogen to water is 2:1. The corresponding mass ratio of hydrogen to water is the combined molar mass of two hydrogens, 2.02 grams per mole, divided by the mass of water, 18.02 grams per mole. The Z subscript for oxygen can only be determined after the masses of carbon and hydrogen are determined. If oxygen is determined to be present, then a subscript can be assigned. A note of caution: there may not be any oxygen present, so do not assume that oxygen is present. Part 1 in the determination of the empirical formula of the organic sample is to determine the mass and number of moles of carbon, determine the mass and number of moles of hydrogen, and finally to determine the mass of oxygen and, if present, the number of moles of oxygen. To determine if there is any oxygen, subtract the masses of carbon and hydrogen from the mass of the original sample. If that number is 0 or close to 0, such as 0.01, then there is no oxygen present. Part 2 in the determination of the empirical formula is to determine the smallest whole number ratio of carbon, hydrogen, and oxygen, if present. This is accomplished by taking the smallest of the 2 or 3 moles and dividing each element's moles by that smallest number. This ensures that one of the elements has a whole number of 1. If you are lucky, all the numbers will be whole numbers, but that is not always the case. If there are fractional numbers, you will have to use a conversion factor to create whole numbers for all the elements. The next slide goes over a few of the conversion factors. If the fractional portion of the moles in the molar ratio is approximately 1/2, then multiply all moles by 2. If the fractional portion is close to 0.33, that is 1/3, or 0.66, that is 2/3, then multiply all moles by 3. If the fractional portion is close to 0.25, that is 1/4, or 0.75, that is 3/4, then multiply all moles by 4. If the fractional portion is close to 0.2, that is 1/5, 0.4, that is 2/5, 0.6, that is 3/5, or 0.8, that is 4/5, then multiply all moles by 5. If the molar mass of the compound is given, there is an alternative approach which will determine the molecular formula more directly. As indicated in Part 2, the process should have gotten to the smallest set of whole numbers. If there are fractions, then convert those according to the table on the previous slide. Part 4 can only be done if the molar mass of the compound is given. If given, determine the mass of the empirical formula that was just found. Then divide the molar mass by the empirical mass. This calculation should result in the whole number, or a number which is remarkably close to being a whole number. If it is not close to a whole number, then the determination of the empirical formula is in error and you must start again. If it is close to a whole number, round the number to the whole number and multiply each subscript in the empirical formula by that number. This results in the molecular formula. You can verify that you have the correct formula by calculating the molar mass of your formula and comparing it to the given formula. If the two numbers are the same or nearly so, then you have probably gotten the correct formula. This is example 1. 18.0 grams of an organic compound is subject to combustion analysis. 29.59 grams of carbon dioxide and 11.31 grams of water are recovered. What is the empirical formula of the compound? What is the molecular formula given the molar mass of approximately 180 grams per mole? First, determine the masses of carbon and hydrogen by using the mass ratios. After that, determine if there is any oxygen by subtracting the masses of carbon and hydrogen from the mass of the original sample. 27.59 grams of carbon dioxide multiplied by 12.01 grams carbon and divided by 44.01 grams carbon dioxide gives 7.529 grams carbon present in the original sample. 11.31 grams water multiplied by 2.20 grams hydrogen and divided by 18.02 grams of water results in 1.268 grams hydrogen in the sample. 118 grams of the sample minus 7.529 grams carbon minus 1.268 grams hydrogen leaves 10 grams of oxygen in the original compound. Next, we need to determine the number of moles present for each element. For carbon, 7.529 grams carbon divided by 12.01 grams per mole gives 0.6269 moles carbon in the compound. For hydrogen, 1.268 grams hydrogen divided by 1.01 grams per mole gives 1.255 moles hydrogen in the compound. Finally, for oxygen, 10 grams oxygen divided by 16 grams per mole gives 0.6250 moles oxygen in the compound. The smallest of these three is 0.6250 moles of oxygen. Thus, we will divide each element's moles to determine a simple ratio. For carbon, 0.6269 divided by 0.6250 is approximately 1 mole of carbon. For hydrogen, 1.255 divided by 0.625 is approximately 2 moles of hydrogen. For oxygen, 0.6250 divided by 0.6250 gives exactly 1 mole of oxygen. Thus, the empirical formula is CH2O. Since we have a molar mass of approximately 180 grams per mole, we can determine the molecular formula. First, determine the empirical mass of CH2O, which is 12.01 plus 2.02 plus 16 equaling 30.03 grams per mole. Taking the molar mass and dividing by the empirical mass, we get 180 divided by 30.03, which is approximately 6. Multiplying each subscript by 6, the molecular formula is C6H12O6. Verify by checking the molar mass of the formula just determined. Example 2, using the alternative method. This example starts by using the previous method first to show that sometimes the first method reaches a sticky spot at the molar ratio. 30.0 grams of an organic compound is subject to combustion analysis. 92.47 grams carbon dioxide and 42.59 grams water are recovered. What is the empirical formula of the compound? What is the molecular formula given the molar mass of approximately 114 grams per mole? Multiplying 92.47 grams carbon dioxide by its mass ratio gives 25.23 grams carbon. Multiplying 42.59 grams water by its mass ratio gives 4.77 grams hydrogen. 30 minus 25.23 minus 44.77 gives 0.00 grams oxygen. Thus, there is no oxygen present in this compound. Taking 25.3 grams carbon and dividing it by its molar mass gives 2.101 moles of carbon. Taking 4.77 grams hydrogen, dividing it by its molar mass gives 4.732 moles of hydrogen. Dividing each of the moles by 2.101 yields 1 mole of carbon and 2.252 moles of hydrogen. Multiplying each by 4 gives an empirical formula of C4H9. The alternative method uses the mass of the original sample and the molar mass of the compound to determine the molecular formula instead of using the empirical mass method. Here, the first set of moles are multiplied by the molar mass and divided by the mass of the original sample. This gives the molecular formula more directly. 2.101 moles carbon times 114 grams per mole and divided by 30 grams gives approximately 8 moles of carbon. 4.732 moles hydrogen times 114 grams per mole and divided by 30 grams gives approximately 18 moles of hydrogen. Putting these together yields a molecular formula of C8H18. Verify by checking the molar mass of the formula just determined.